Okay, so let's talk about the greenhouse effect. We're just going to jump right into our PowerPoint. Um, so we started talking about this today with our simulation, so this should seem fairly familiar. So we're just going to move through this fairly quickly. So the greenhouse effect starts with solar radiation. That is energy coming in from the sun. But not all of the radiation from the sun actually reaches the Earth's surface. So some of our solar radiation is going to be reflected by the atmosphere. And then some, that's about 25%, is going to get reflected back into space by clouds or by the atmosphere. 19% is actually going to get absorbed by the atmosphere and the clouds, but that's still going to get radiated, some of it down to Earth and some of it back out into space. So that's not reflected, but absorbed, changed into a different form of energy, and then radiated. And then the rest of it, so we're looking at about 55% of it here, is going to reach Earth's surface. And once it reaches Earth's surface, one of two things can happen. It can either be absorbed or it can be reflected. And whether or not it is reflected depends on essentially the color of the surface that it strikes. So the lighter it is, the more likely it is to be reflected, and that we call albedo. Lower albedo surfaces are darker surfaces, so things like soil or open water. They absorb sunlight, and then they're going to release that in the form of infrared radiation rather than visible light, infrared radiation, which we sense as warmth. Our higher albedo surfaces, so things like ice and snow and light colored surfaces, are going to reflect more of that sunlight directly back out into space or into clouds or greenhouse gases that absorb it. But most of it's going to go back out into space. So that infrared radiation, that's the part that the greenhouse gases really have a lot to do with. So what is the greenhouse effect? Well, the gases in Earth's atmosphere, specifically the ones we refer to as greenhouse gases, trap that infrared radiation rather than allowing it to pass through those gases and back out into space. They radiate it back down to Earth. Now, it's important to recognize that we need the greenhouse effect. Without the greenhouse effect, Earth is going to be too cold to support life. Just like we can't grow plants here in the winter without a greenhouse, we couldn't survive on Earth without the greenhouse effect. So how does it work? Well, that incoming radiation gets absorbed by the Earth, by those low albedo surfaces, and it heats up. And then the Earth's surface releases that heat in the form of infrared radiation. So now we've had light come in, impact the surface, gets absorbed and released as infrared radiation. And the greenhouse gases absorb that infrared radiation and radiate some of it out into space and some of it back towards Earth. The portion that comes back to the Earth is the portion that we call the greenhouse effect. So what are our most important greenhouse gases? What are these gases that are responsible for trapping this heat? Well, the one that we talk about most often probably is carbon dioxide. Where does it come from? It comes from the combustion of fossil fuels, but it also comes from decomposition. Aerobic decomposition, we've talked about this, produces carbon dioxide. We also talk about deforestation as a contributor to carbon dioxide because depending on what's done with those trees, the trees themselves are going to release the carbon dioxide, but they're also no longer absorbing carbon dioxide. And we know that large forests, especially old growth forests, are what we call carbon sinks. And so they absorb and hold on to that carbon dioxide. So when we cut down those forests, we take away that sink. The second one we're going to talk about is methane. So methane, of course, is the primary component of natural gas. So we have methane escaping into the atmosphere as a byproduct of natural gas extraction. Also animal agriculture, animals as part of their cellular respiration tends to be anaerobic, and so they emit methane as part of that respiration. And then anaerobic decomposition. So this could be decomposition in swamps. This could be anaerobic decomposition at wastewater treatment plants. But one of the big contributors now, as the globe is warming, is thawing permafrost. So that permafrost that has been frozen for so long, there's lots of organic material, and it's decomposing in an anaerobic environment and contributing to methane in the atmosphere. Third one is nitrous oxide. So this is N2O. This is not the nitrogen oxides that we've been talking about as a byproduct of fossil fuel combustion, although it sometimes can be. Primarily, nitrous oxide comes from the denitrification of nitrate. So it comes from agricultural soils, particularly in overwatered soils because it's now anaerobic. And over fertilized soils because there's lots of nitrogen there. So nitrous oxide primarily comes from agricultural soil. And then, as we talked about with the ozone layer, the CFCs and the HCFCs and the HFCs. So those chlorofluorocarbons, those hydrochlorofluorocarbons, and those hydrofluorocarbons are all greenhouse gases, and they're really potent greenhouse gases. Water vapor is technically a greenhouse gas, but water vapor does not have a long dwelling time in the atmosphere. So it doesn't stay in the atmosphere for very long. It is controlled by the water cycle. So it doesn't really drive atmospheric temperature change. In fact, atmospheric temperature change drives the water cycle. As the atmosphere gets warmer, more water vapor is brought into the air. So let's talk about those four and their global warming potential, which we abbreviate GWP. So global warming potential is just a measurement of how much a given molecule of gas can contribute to the warming of the atmosphere over a 100-year period. So it's a very specific definition. Over 100 years, how much can this contribute to warming as compared to carbon dioxide? And so because we compare to carbon dioxide, we set carbon dioxide as 1. So this is really based on two factors. So the global warming potential is dependent on these two things. The first one is residence time. That's how long the molecule stays in the atmosphere. So just like persistent organic pollutants are a problem because they stay in the environment for a long time, the longer a greenhouse gas stays in the atmosphere, the larger its impact is going to be over those 100 years. And then the second impact is infrared absorption. And this is how well the gas absorbs and radiates infrared radiation. So combination of those two tells us the global warming potential of any of our greenhouse gases. So because carbon dioxide is the thing to which we compare all other greenhouse gases, we assign it a global warming potential of 1. Methane is the second global warming potential. It remains in the atmosphere around 12 years, so it has a relatively short residence time, but it does absorb more IR, more infrared radiation than carbon dioxide does. And so it's assigned a global warming potential between 23 and 84. Usually it's somewhere in the mid 20s, 28 to 34. And again, this just depends on who's doing the measuring. Next one, nitrous oxide. So nitrous oxide has a really, really long dwelling time or residence time. It remains in the atmosphere around 115 years, and it absorbs much more infrared radiation than carbon dioxide does and radiates that back. So it actually has a global warming potential of around 300. So huge, huge increase there, 300 times more damaging than carbon dioxide. And then the last one that we talked about is CFCs. And CFCs remain in the atmosphere most of the time 50 to 100 years. They can last as long as 500 years, depending on the chain length. and they absorb much, much, much more infrared radiation than carbon dioxide. So they have a global warming potential between 1,600 and 13,000. It's not important that you guys know the exact numbers, but it is important that you know, relatively speaking, that carbon dioxide has the lowest global warming potential, followed by methane, followed by nitrous oxide, and exceeded by CFCs. So again, it's important that you know relative strength, not absolute numbers. Okay, we're going to skip the practice FRQ and we'll do that in class. All right, so now let's talk about what is contributing to these increases in greenhouse gases. I feel like I skipped a slide. Okay. So why is sea level rising? Number one reason sea level is rising is thermal expansion. So you guys probably remember from chemistry class that when things are heated, their molecules spread farther apart. So this is true of water as well. When water molecules are warmer, they are farther apart. So that means that water at a higher temperature, it takes up more volume. So the ocean has a lot of water molecules in it. So even a small thermal expansion is going to lead to a pretty significant sea level rise, or certainly measurable. And this is the one that we all think of, melting polar and glacial ice. As we have increased greenhouse gases and we have increased atmospheric temperatures, we have a warmer climate, and the ice sheets at the poles and glaciers are melting. That water has to go somewhere. It winds up in the ocean, and that leads to sea level rise. So these two combined create this significant change that you can see in this graph. What's the impact of the rising sea level? Well, a lot of different impacts. Environmentally, we have significant flooding of coastal ecosystems like our estuaries, those mangroves, those salt marshes. And as we talked about, these are the nurseries for many of our marine animals. And so flooding those ecosystems is going to lead to reduced populations. It's also going to lead to a loss of species that depend on Arctic and tundra ecosystems, because that freeze-thaw cycle that glaciers go through provides ecosystems and human communities with water. So we can see this is an image taken 63 years apart, and you can see how much that glacier has receded. When we talk about human impacts, obviously, if we have significant sea level rise, and certainly we are right here in the thick of this, our coastal populations are going to have to move. Those beach homes are no longer going to be safe. We're going to have an increase in the frequency of flooding, which results in higher insurance and repair costs. It results in lost property, and it can cause a decrease in property values as well. And then, as we talked about when we talked about water, there's also the issue of saltwater intrusion, which is where saltwater infiltrates into the aquifers and contaminates our groundwater and our wells. Okay, another significant impact of the increasing global temperatures is the impact on disease vectors. So like we talked about in last unit with pathogens, vectors are these living organisms that can transmit diseases from human to human or from animal to human. So we're usually talking about insects, mosquitoes, ticks, fleas. So diseases like malaria and West Nile virus, even dengue fever and cholera, can be transmitted via vectors. And vectors, generally speaking, prefer warmer environments and moister environments. And so as the warmer temperatures spread around the globe, they allow these insect transmitted diseases to spread to parts of the world that were previously too cold for these insect vectors. So as they expand their range further out from the equators, new human populations are at risk. So here's an example of the mosquito that carries dengue fever, Zika virus, and yellow fever. And its range is expanding. Okay, and that's it for this topic. So as always, if you have questions, let me know, and we'll start class tomorrow with practice FRQs.